Jem uses G-force to achieve a face drop. Dallas is zapped with a ray gun.
What I didn't tell you is that sitting above the box is my specially constructed death ray.
No, you failed to mention it.
And I break into a sweat in the name of sport relief.
Pain is my friend! Pain is my friend! Pain is my friend. I feel no nerve. Ow!
That's Bango's theory, putting science to the test.
Welcome to tonight's show. Thanks for joining us. We've got a packed show as ever. But first up, we've got to settle a little bit of unfinished business.
You might remember last week I built myself a little fire extinguisher powered dragster. Absolutely the best bit about that machine was testing the launch system. I pulled over 3.5 G for nearly a second, which not only feels amazing, it left me wanting to know a lot more about the effects of acceleration on the human body. G-force is a term we use to relate the forces we feel due to gravity to those we experience from accelerating or decelerating. At the moment, I'm experiencing 1G, not because I'm accelerating, but because gravity is trying to pull me down. Now, if I want to change those G-forces, I either need to change gravity, which is very hard, or I need to accelerate, which is a lot easier. Whilst in freefall, I'm accelerating downwards, just going with gravity, so I feel effectively weightless. But when the bungee snaps tight, I start decelerating rapidly. That deceleration makes me feel twice my normal weight, and upside down, that's really quite unpleasant. But I suspect you can feel very similar G-forces much closer to home, so I want to find a way of measuring the effects of acceleration in everyday life. This set of scales actually makes a pretty handy G-force meter. Now at the moment, the Apple is exerting a force on these due to gravity of about 200 grams. That's a 1G situation then. Now, if the Apple exerted 400 grams, that'd be 2Gs it'd be pulling. And 600 grams, 3G. But if I give it a bit of acceleration, you'll see there's extra forces at play. Yep. Its apparent weight changes, and I can see how many G's it's pulling due to that change in weight. Right, time to take it into the field. For the first test, all I need is a couple of friends and a roundabout. Right, we're getting up to like 1.5, 2G there. Oh, that's better, yeah, you're feeling it there, that's almost up to 2G. Right. Right, that was a sustained 2G. And now we're off to the swings. Right at the top, I'm kind of partly weightless. Down at the bottom, I'm putting maximum G, and it's just over 2G. On a standard child swing. And the final, not to be repeated at home test, a tall tree. As human beings, we regularly experience a wide variety of G-forces, the most extreme of which are when we come to a sudden stop. There was some pretty rapid deceleration, and it looked to flick up to about 6G there, but only for an instant. How long can a human survive high Gs like that for? One way to find out would be to attach myself to a rocket sled. Sounds like a death sentence? Well, there is one man who tried it. The legendary Colonel Stapp, the world's first crash test dummy. A At the end of the track, he experienced a deceleration of 25G for almost 2 seconds. It burst all the capillaries in his eyeballs, which is why I don't fancy doing what he did. But I do want to do this. This centrifuge dates from the 1950s. Since then, thousands of fighter pilots have experienced extreme G-forces, enough to make them go unconscious. So it's time for me to take a spin. I can't believe I'm going to be spinning in that. I knew it was some sort of oversized roundabout, but the scale of it is simply absurd. Right. This is it.
Problem and Regal.
Aviation specialist Dr. Mike Glanfield is going to make sure that I stay in one piece as I'm spun around.
Ready for takeoff.
Okay, Jen, we're just about to start. Any questions?
Yeah, what am I going to feel? What's going to happen to me?
Well, although we're not going very fast in terms of miles per hour, you may experience symptoms of grey out or even loss of vision if the G level is high enough.
Okay, slightly nervous.
So first, Mike is going to start me off slowly and subject me to 2.8G. Although less than I experienced on my fire extinguisher car, that was only for a few moments. This is going to be for 15 seconds.
2.8G, 15 seconds.
Here we go. Oh, I feel that. Maintaining this level of acceleration for such a long period has a much more profound effect on my body.
My arms just feel so weirdly heavy. That's astonishing. Look how quickly they come down. There's no effort from me there at all. Oh. It's just great. Absolutely great. Let's go again.
2.8G is not far off what you can expect on some fairground rides. But for real pain, Mike's going to spin me at almost 5G, the highest I can go without going through proper pilot training. This is going into crash test dummy territory.
I must be looking forward to this. Okay, relax.
As the needle crept up, things started to get a bit nasty.
I feel my face sagging. Like I feel as though I probably look about 10 years older. I feel ridiculous.
At this point, I feel like I weigh 400 kilos, but worse still, the blood is being flung away from my head and into my feet, with devastating consequences.
Okay, my vision's going there. Oh, that almost went completely black then.
Another couple of seconds and I'd have been out cold.
Well, at least now you know what you look like at 60, love.
Slightly harsh, thank you.
Gotta see that face again. Gotta see it. Look at that. It's a thing of beauty.
It is a beautiful thing. Okay, coming up next is Dr. Yan. This week, he's got old Steve Zissou on us. Snorkels are great, but they only let you stay at the surface. Have you ever wondered why you don't get really long snorkels that allow you to go down deep?
Yes, I suppose so. I haven't really thought about it, but yeah, impractical. So the pressure.
There are several problems. Here's the first one. If I take a really long snorkel here, what do you want to do? I said it's perfectly clean, don't worry, and just breathe out this. Now, at the start it's fine, but if you had your nose blocked, after a while I suspect you're going to go. It's going to get a lot more difficult. That's because when you breathe out, all that air is just staying in the tube. And then you breathe it all back in again, so you never get any fresh air. If I cut the tube down though, so that I can get some fresh air, there's still a major problem when I take it underwater. Watch this. someone's holding the end of the tube or pushing in on it or something. The problem is that water's pretty heavy stuff, and so as soon as you go under, it's pressing in on your body. And for me to be able to breathe the air up here when I'm down there through this tube means I have to push out against all the pressure of that water, and I don't have to go very deep before that becomes just impossible. Watch this. So imagine that these bottles represent my lungs, and this one I've given a really long snorkel to, and this one with the lid on is like when I'm holding my breath going underwater. Watch what happens. Look at that. Look how much pressure there was down there. And it's not even that deep. It's not surprising I couldn't expand my lungs against that. But if you look at the air in this bottle, like the air in my lungs when I'm holding my breath, it gets put under greater pressure as it goes down, and that helps resist the crushing pressure of the water. There is one animal, though, that has special ways of dealing with this, and can snorkel several meters underwater. Believe it or not, elephants regularly snorkel using their tongues, and they have specially strong muscles to fill their lungs underwater. And crucially, they also have specially thick linings to their lungs which protect their blood vessels and stop the blood bursting out into their lungs under the pressure. Now, you don't want that happening to you, so be careful. Don't go deep underwater with a long snorkel.
And that, Dallas Campbell, is why elephants rock.
And it's why Yan rocks as well.
Totally. Now, Dallas, can I show you something very cool?
You can.
Scientists in Ecuador have discovered this brand new species of gecko. It's called Lepidoplophis bushwaldi, and a fully fully grown adult sits on the end of a pencil.
That's tiny.
How cute is that?
How do they find that?
I know, amazing.
Cute, but not ridiculously small. For that, have a look at this.
Yes. What is it?
Well, artist Willard Wigan has been making sculptures from grains of sand, shards of glass, and even spider's web. Sculptures so small he can fit them in the eye of a needle. But more, he then paints them with the hair off a housefly.
I tell you what, I'm obsessed by this guy. He actually has to work in between heartbeats in order to do it, and sometimes he inhales his own work. He's amazing. But if you want really, really small, we have to go beyond microscopic. Prepare to have your mind well and truly boggled. Welcome to the crazy, mixed-up world of the atom. So let's start at the beginning. I just want to try and give you a sense of just how ridiculously tiny atoms are. So have a look at these grains of sand on my finger. Now they're pretty small. Each one's about 1/10 of a millimeter across. And yet each one of those grains of sand contains 1 billion trillion atoms. Just try and imagine that, 1 billion trillion atoms. And if I was to expand one of those grains of sand, so let's say it was the size of this beach, about 1 kilometre or so across, you would just about make out the individual atoms, and they'd look like one of those grains of sand. Atoms are very small. But even though atoms are so small, we know a remarkable amount about them. For instance, we even know how many atoms there are in the entire universe, give or take 1 or 2. And given the enormity of the universe and the minuteness of the atom, it's an incredibly big number. It's 1 followed by over 80 zeros. That's 100 million trillion 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 atoms. That's an unimaginably big number. To get a sense of it, compare it to this other unimaginable number, the number of single seconds since the beginning of the universe. That's only a few 100,000 trillion, so you're still short by a factor of 1,000 trillion, 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 trillion. Okay, so we know that atoms are really, really tiny, and we know there's lots of them. That's all fine and dandy. But here's the really weird thing. They're almost completely empty. Have a little look at this. Okay, go, go, go! Now, you may remember from your school physics that the atom is made up of several different parts. So you've got your hard nucleus in the middle, which is played by Louise there on the pink moped, and whizzing around that you've got the electrons, which are the little light bits. Now that all looks nice, but it turns out that that scale is completely wrong, because if the nucleus was the size of Louise, those electrons would be 50 kilometers away, and they'd weigh about 3 grams, which is the size of this little pebble. Atoms are almost completely empty.
Let me explain this another way.
If you could somehow remove that empty space from an atom, it would be impossibly tiny. In fact, if you removed all the empty space from all the atoms of all the people on Earth, you could reduce the entire human population, all 6.8 billion of us, to the size of this apple, or this pasty.
The fact that atoms are empty may feel weird, but that's actually just the beginning. As scientists found out more and more about atoms, they discovered to their own discomfort that they were weirder and more contradictory than they had ever imagined. So they came up with a theory to explain how atoms work, and they called it quantum mechanics. It's so weird that the great physicist Richard Feynman once said, if you think you understand quantum mechanics, you don't understand quantum mechanics. Albert Einstein himself hated it. So to try and wrap my own brain around this idea, I've come to meet Jim Al-Khalili, master of quantum mechanics, to learn how physicists make sense of the atom.
The best way to visualize atoms is to think of an atom as being like a cloud of possibilities, like it's sort of a fuzzy cloud of atomness spread out over space. And then when you look, you collapse it and force it to make up its mind where it wants to be. So you can never catch it being this fuzzy spread out cloud.
Back on the beach, thanks to quantum mechanics, our simple model of the atom now has to change radically. Jim's cloud of possibility means that all the bits of the atom, the electrons and the nucleus, aren't in a single place, they're in many places at the same time. And they say, it's only when we look for them that, pow, they somehow decide where they actually are. But don't worry if this sounds too strange to believe. It freaks out most scientists too. And to show me just how odd quantum mechanics is, Jim wants me to take part in a famous thought experiment in a cupboard.
So,
Okay.
close the door.
Yep.
Alright, Jim, I'm in.
Right.
What I didn't tell you, of course, is that sitting above the box is my specially constructed death ray.
No, you failed to mention that.
Now, don't worry too much,
Okay.
but basically quantum mechanics says that an atom can be in two places at once. Now I've got an atom hooked up so that if it's in one location, it triggers the death ray, which destroys everything inside the box. And if it's in another location, it doesn't trigger the death ray and you'll be fine. You with me?
Okay.
This means that you are now both dead and alive at the same time, until I open the box and check whether you're okay. And you're fine.
See, I'm struggling with that still, because I mean, I understand the sort of idea behind it in the sort of Lion Witch and the radioactive wardrobe scenario, but clearly I'm alive.
Yeah. Well, the thing is, atoms are doubly sneaky, because an atom not only can do two things at once, but it seems that weirdness is restricted down to the level of atoms. So in reality, you are never both dead and alive at the same time, because that weirdness of where an atom being in two places at once is constrained down to the level of atoms, and we don't see it in the everyday world.
No, I guess that's the point. I think a lot of people think that it's perhaps some kind of esoteric, spurious notion, but it is in fact the bedrock of modern physics is this.
Yeah, Albert Einstein himself had problems with what quantum mechanics was saying about the world of atoms.
Yeah.
The reason why we put up with this weirdness is that quantum mechanics is the most powerful, the most accurate, the most successful theory in the whole of science. Without it, we wouldn't have most of modern physics, we wouldn't have modern chemistry, we wouldn't have modern electronics, we wouldn't have computers, we wouldn't have the Large Hadron Collider, we wouldn't even know why the sun shines.
So basically I'm just going to have to accept this and learn to love it.
I think so. I think it's a small price to pay for the most powerful theory in science.
You see, Dallas, I still find quantum physics the most difficult science to get my head around, but Jim very nearly convinced me there.
Yeah, but you know what? You're in really good company because everybody finds it difficult to understand. Because it's counterintuitive, it's weird, but saying that, it's still utterly beautiful and fascinating to think about.
But enough of the theoretical science for the time being. Can you cope with that?
I can.
Okay, time to get physical. If you're watching the Sports Relief Mile, you may have noticed a few familiar faces sweating it out amongst the runners.
And I decided to put on our running gear and get all sweaty in the name of charity.
It wasn't pretty, but in true Bang style, we needed to add a bit of science to the mix. So we wanted to find out if a series of experiments could predict exactly how fast we could run that mile. So before we ran it, we headed to the lab, didn't we? The human body is an amazing piece of machinery, and scientists in places like this, Brunel University Centre for Sports Medicine, are dedicated to fine-tuning that machinery to the max. So this is a perfect place to find out if Mr. Dallas Campbell, a fine specimen of a man, is operating anywhere near his full potential. Whoa. Right, Dallas, this is Dr. Lee Romer. Say hello, boys.
Nice to meet you.
Now, Lee has helped some of the country's top athletes to win Olympic medals, and he's going to put you through your paces today using all those pieces of snazzy scientific kit so we can predict exactly how fast you can run the Sports Relief Mile. Are you psyched?
I am sort of psyched.
That's good enough for me. Now, knowing your ridiculously competitive streak, I thought we'd need to up the ante. And I think the last thing you want is for a girl to beat you. So I'm going to compete with you today.
I like the sound of, are you going to be doing it in your heels?
In my heels and my way jumper.
Nice.
No,
I think you look the part for that.
Not really.
I'm ready for the challenge. Bring it on.
I'm quite happy that you're not laughing at me, Dallas
Come
Campbell.
on, let's get on with it.
You go first. The first test is to run a series of short bursts and then a final blitz. Now, when you exercise, your body has to perform an enormous amount of work. You've got your heart, your lungs, and your muscles all operating flat out. And it's the efficiency of these various systems all working together that can determine exactly how fast you can run. And that's what Lee is going to be measuring to predict our mile times. It'll push me and Dallas to our limits. But the other thing that Lee is testing is how long our muscles can handle the exercise before feeling the pain. Now, normally, when you go about your business or taking a light bit of exercise, your body gets its energy predominantly from a process called aerobic respiration. It uses oxygen to burn up sugars, giving energy to the muscles. But when we ask the muscles to work harder above a certain level, they can't get energy quickly enough through aerobic respiration alone. So cells in the muscles start producing energy by burning up sugars without oxygen in a process called anaerobic respiration. And there's a downside to this, as it creates some nasty byproducts like lactic acid. It's when that acid builds up in the bloodstream that we really feel the pain. And unfortunately, measuring it is a bit painful too. So Lee, the build-up of the lactic acid, is that an indication of when we hit the pain barrier?
That's right. It's basically the breakdown of all the metabolic byproducts that's feeding back to the brain, telling you, hey, slow down, this is getting hard work. Keep working. Keep working.
You can do it, Dallas. Come on.
And stop.
Well done. Well done.
Do you have the time, Chris?
Oh, thanks. That was hard work. Blimey.
On a scale of 1 to 10, how much fun were you having?
-20.
And then it was my turn. Before long, I was beginning to understand what the pain of lactic acid is all about. And then Lee turned up the speed.
So you're so nearly there. Come on, Liz. Come on, last few seconds.
Nice and relaxed.
Okay, hold on to it now. Hold on. We're going to go up again. Keep forward. You're in charge. Okay, and relax.
Lee then ran a lactate analysis on the 6 blood samples he'd taken from me and Dallas, and it was time for the results.
Okay, well, you both did really well. Really good efforts all round.
Alright, let's talk about the lactate in particular. How are we doing with that?
Okay, if you look on the figure there behind you, this is Dallas's data, and on the horizontal axis at the bottom there is the increase in treadmill speed,
Yeah.
and on the vertical axis it's the blood lactate concentration, that we're measuring actually from the earlobe here. And you can see that it increases quite sort of steadily down here, and then it starts to shoot up towards the end. So although it's not completely obvious, a threshold may be occurring at about here where you're transitioning from primarily aerobic to anaerobic. So that's around about 12 kilometers an hour.
Okay, so that's the
pretty good.
lactate threshold, which is where your body's beginning to struggle. There's more lactate in the system than can be cleared, so your muscles are going to feel it.
That's right.
Okay, that's not too shabby. That's at like 12 kilometers an hour or thereabouts.
That's not bad.
So he's fairly fit, right?
That's not bad. Should we have a look at yours? Okay, so this is Liz's day. It's a kind of similar shape. You can see a threshold's probably occurring about 9 kilometers an hour.
Oh, rubbish.
So-
longer legs.
So I reached my lactate threshold much earlier on during...
That's right.
The speed
At a lower running
increase.
speed.
Seriously?
But you can train it. You can certainly improve those figures.
How does all this translate into a mile time?
Okay, well, there's your time, Dallas. So that's an average. There's going to be a little bit of variation, but it's not a bad predictor.
That's
Nancy
pretty
Bannister
good.
will be quaking.
I know I have to see mine, so just go for it. I'm thinking probably around 9.
Okay, let's have a look.
I can live with that.
That's still pretty good.
I can live with that. We've only got a week till the Sports Relief Mile, so we can't really improve it with physical training. But there is a way we can probably knock a few seconds off.
How?
I'm going to show you. The power of the mind also has a lot to do with winning races, something that UK 400-metre record holder Ewan Thomas knows a thing or two about.
Going to talk to you about running quickly.
You are.
Trying to help you anyway. A race of 8 guys, it wasn't always the sort of physically fittest or the fastest would win. Out of those 8, probably whoever kept their nerve and stuck to the game plan the most would win the race.
Really?
Psychology is huge. First of all, it isn't rocket science. You can do it, right? Listen to music to fire yourselves up, to be mentally ready.
Yeah.
Set a realistic goal. Realise at some stage in the race it is going to hurt, but pain is your friend. Yeah?
Pain is my friend. Pain is my friend.
Pain is my friend.
I feel no nerves. Ow.
Pain is weakness leaving the body. Yeah? That's all
I
it
like
is.
that.
Yeah.
Ooh, that's a good one. Right.
Do it.
Do you reckon we're ready?
You're ready. You look ready. You look ready. Let's do it.
You're a star. Thanks
Good
a
luck.
million.
Good luck.
I hate you. We will see you next week. See ya.
Bye.
Goodbye.